So the bacteroids. This is one of those groups where I don't usually know what to call them. The sphingobacteria is another name for this group. The bacteroids are another. Traditionally, it's been called the Bacteroides Flavobacterium cytophaga group. There just isn't a very good name for it. I'll probably try to call them the sphingobacteria. Bacteroids is specific kind of for Bacteroides, and at least superficially excludes the other, which isn't really right. This is a group of organisms. It's actually quite a big group and pretty abundant in the environment. But most of these bacteria are going to be unfamiliar to you because there aren't a lot of pathogens in this group, and there aren't a lot of industrially or ecologically important organisms in this group, at least from the human perspective. An exception to that is this organism itself, Bacteroides, which is a major component of your gut flora. Depending on your diet, from something like 1/4 to 3/4. This group of organisms falls into three major classes: the bacteroids, the flavobacteria, and the sphingobacteria. And these are also generally phenotypic groups as well. So the bacteroids, these are all heterotrophs. They're generally mesophilic. They're generally rod-shaped as well. The bacteroids are anaerobic and live on sugar, released from usually complex polysaccharides. Likewise, the sphingobacteria, by the way. The flavobacteria, the sphingobacteria are aerobes. These are anaerobic polysaccharide degraders. These are aerobic polysaccharide degraders. And the flavobacteria are also aerobes. And the flavo comes from the fact that they oftentimes have pigments. So here's Bacteroides. This is Bacteroides theta iota omicron. It's one of those things where it started out as Greek letters and they were just typed out. Very weird. If you eat a high starch diet, particularly a vegetarian diet, for example, these things are the primary things in your gut. The more carnivorous you are, the more Clostridium you have in your gut, or the more protein you eat. Bacteroides fragilis and other relatives are big ones. Bacteroides fragilis is an opportunistic pathogen, but in most people it's perfectly harmless. Theta iota omicron and its relatives are the primary ones. And they're the ones that hyperlyze the starch that you eat and turn that into sugar that the organisms in your body can use. The flavobacteria, obviously aerobic. They're typically yellow, long rods with tapered ends, as is common in this group. These organisms can also hydrolyze starch, but generally can also hydrolyze other kinds of polymeric sugars as well. Things like DNA, things like chitin, agar, gelatin. Those of you who have yellow colonnades on your agar degrading plates almost certainly have flavobacterium. If they're white, then they're probably sphingobacteria, which we'll talk about in just a moment. These organisms are inherently resistant to a number of antibiotics, including the beta-lactams. This has to do with their target. There's no resistance gene. It's just that the target protein doesn't bind beta-lactam antibiotics. And as a result, you might think they would be terrible opportunistic pathogens, and kind of like MRSA. But in reality, not many of them are good pathogens at all. There are a few. The primary one is Flavobacterium johnsonii, which is a problem for the fisheries industry. And so any place you have a lot of fish together in one place, in crappy environments, you're likely to have Flavobacterium cause fish kills. It's a chitin degrader, and this is one of the things it does, is that it eats not just chitin, but the other polysaccharides on the fish. It's a rapid glider. Interestingly, it can only glide over surfaces. It can't glide through liquid environments. This has to do with this mechanism of dividing, which we'll talk about in just a minute. It doesn't show up very well on here, but this shows it's an example of pleomorphism in bacteria. So sometimes you see, particularly those of you who have interesting agar degraders, like in the lab part of this class, or the lab class, is that you'll pick a colony and you'll see big cocci and you'll see long rods, and you'll be dismayed that you haven't got your organism pure. And you pick a single colony and you streak it out and you see the same thing. And you pick a single colony and you streak it out again and you see the same thing. The reason is that those are two different forms of the same organism, like this and this. Resting phase cells in stationary phase are cocci, and the growing cells are rod-shaped. If you look at E. coli, you can see the difference between logarithmically growing and stationary phase E. coli, but they're relatively subtle. In this group of organisms, this pleomorphism is usually pretty dramatic. And you see huge differences in the appearance of cells based on how fast they're growing. Last are the sphingobacteria. And so Cytophaga is kind of the traditional one of these. These things are generally pleomorphic and can eat a large range of polysaccharides like the Flabobacterium. These are non-pigmented though, long, thin, flexible rods or short rods, and they eat things like cellulose and chitin agar and that sort of thing. They oftentimes form side-by-side monolayers, so it doesn't show up very well here, but the cells arrange themselves side by side rather than end to end. We talked about this on Cytophaga hutchinsonii is a cellulose degrader. So these are cellulose fibers that are all covered. The cells are in contact with them, they glue themselves to the cellulose, and then secrete hydrolases that eat the polysaccharide. Because they can't internalize these large polymers, when they hydrolyze it, those sugars diffuse out, right? And so now they're where the sugar is at the highest concentration, so they get the bulk of it. But a fair bit of sugar does leak out into the environment. As a result, they can feed a complex community of other organisms.